Welcome back to this lecture series on pulse width modulation for power electronic converters. So, we have been looking through various course modules. These are first couple of, I am trying to organize the course modules for your understanding. So, you have this overview of power electronic converters was one of the first module that we saw, where we looked at different topologies of power electronic converters, and then we looked at different applications of voltage source converters such as motor drive, active front end converter, and reactive power compensator. So, these are somewhat like a typical power electronics course. These two modules fall under somewhat typical power electronic courses, and where you could have some overlap with other things, but we just did this so that if we want to do pulse width modulation of power converters, we need to be clear what the power converters are and what they are going to be used. So, then the second set of modules, this is actually would be second set of modules, they are more about pulse width modulation. So, about Fourier series and how you would switch them, various symmetries, how you would generate the pulse width modulation waveforms at low switching frequency, and how you would do it with the high switching frequency. So, the last two are more to do with the high switching frequencies. This is based on the classical way of comparing 3-phase modulating signals against triangular carrier, and this is relatively more modern of getting through space vector based PWM. So, this comes from the modulation theory that they have used in communication and so on. This basically originates from electric machines. So, though their origins are different, there is a lot of similarity between the two, which has been established in the literature, and we also saw that now. So, everything that is done by the triangle comparison PWM can also be done by space vector. The only difference what we say in this course is certain things done by space vector cannot be done by triangle comparison approach. And so, there are methods called continuous PWM methods, which can be implemented either using the former approach or the latter approach. There are discontinuous PWM methods or bus clamping PWM methods, which can be implemented either using a triangle comparison approach or space vector approach, but there are those advanced bus clamping PWM methods which normally cannot be produced by comparing 3-phase modulating waves against triangular carrier. They need the space vector. So, in some sense space vector based PWM is more general than the triangle comparison based PWM. So, in the triangle comparison based PWM, what you do is you have 3-phase sinusoids, you also add common mode components. Addition of common mode component to the 3-phase sine waves is equivalent to dividing the null vector time. See, when you in every subcycle we apply two active vectors and a null vector, and the null vector is applied through two different 0 states in the inverter. When the one 0 state is when all the top switches are on, other one is when all the bottom switches are on. So, it is the division of active vector null vector time that we have seen, that is really the degree of freedom available. But in space vector based PWM, we not only do that, we also divide the active vector time. It is also possible to apply an active state more than once, multiple application of active state, and you can so called division of active vector time could be done. So, the advanced bus clamping PWM methods, they do that, they apply only one active, only one 0 state, but they apply one of the active states twice, and they produce some interesting waveforms, and they are capable of improving the performance particularly at high modulation indices and so on and so forth at some level now. So, let us go on from that is the second set of module, and the third set of modules we have been more into analysis. That is, earlier the focus was more on generating the given amount of PWM waveform and maybe enhancing the DC bus utilization for a given amount of DC voltage, how much AC voltage you can produce. So, that is one of the reason why we went in for common mode injection and so on. Now, the emphasis shifts more to the harmonic components, not just the fundamental component. The harmonic components in the voltage lead to harmonic currents, and these are at various frequencies, and so the sum of all the harmonic currents you can turn them as the current ripple, and we try to analyze the current ripple. So, we try to come up with methods of calculating the RMS current ripple, particularly considering the high switching frequency case. So, we consider the error between the applied voltage vector and the reference voltage vector and integrate that and try to evaluate that now. Then we did the DC link current analysis. So, the AC side you may have sinusoidal currents with little ripple flowing there. Now, the DC link current is basically the sum of the top switch currents, and every top switch current is the product of that switching function and the current that is flowing through that leg. So, we try to analyze the DC link current, so which has a DC component and has harmonic components. and the DC component flows from the DC side, and most of the harmonic the DC side I mean the power supply. Let us say there is a rectifier or battery or some active front end converter, so on, and the harmonic components in the DC link current largely flow through the capacitors, DC electrolytic capacitors. The electrolytic capacitors are the main sources for the ripple component in this DC link current, and therefore we evaluated that so as to be able to evaluate how much ripple current the DC capacitors should give us. So, we looked at these kinds of analysis, one is from the line current ripple and then the DC link current. Then we looked at torque ripple, because we are considering induction motor drive as our main application here. And so, in the induction motor drive, when you apply harmonic voltages, it causes harmonic currents, harmonic fluxes, and there are also harmonic torques. And we found that the harmonic torques are normally caused by interaction of fundamental flux with some harmonic current or fundamental current with harmonic flux. So, we tried to analyze this torque ripple considering two cases, when you had low switching frequency and when you have high switching frequency. Then we looked at evaluating the inverter loss. So, up to this point we regarded the devices as ideal. Here we started considering the forward drop in the device and tried to calculate the conduction loss. Again we tried to look at the transitions in the devices, turn on turn off transitions and the energy that is lost, and calculate the switching energy loss. And we also worked out some PWM methods which are capable of reducing the inverter switching loss compared to conventional space vector PWM. Interestingly, bus clamping PWM methods and some advanced bus clamping PWM methods are capable of doing that. So, like our in this module we had 3 lectures, the first one focusing on conduction loss, second focusing on switching loss, and the third one exclusively focused on this reduction. And we looked at this advanced bus clamping PWM methods, we saw how they could probably be used, there were at least some directions in that regard, how they could be used to reduce the inverter switching frequency. So, this is there is inverter switching loss and also the power conversion loss. Alright. So, this is now kind of little bit of analytical on these issues now, and now you have the other set of modules which I would call as the last set of modules. So, the overall there are 13 modules, I am now putting them as 4 sets for your easy understanding. So, here this is a little I would call them as slightly complex, in the sense like we were not considering the inverter switching transitions at all, and then they at some stage we started considering them, that is in the previous stage we started considering, for example, the switching loss and so on. Here we are considering the effect of dead time, that is the dead time is like the top and the bottom devices are not exactly complementary in an actual inverter, not switched complementarily. You switch off the outgoing device first and then you switch on the incoming device which is on dead time, and we looked at what are the effects of the dead time. We found that the dead time analyzed its effect for continuous PWM methods. We found that for all continuous PWM methods the effect of dead time is quite similar and it was dependent on power factor. And we also looked at the effect of dead time for bus clamping PWM methods. We found that the dead time effect under a given condition changes from one bus clamping PWM to another bus clamping PWM, and also for the same bus clamping PWM the dead time effect varies from one power factor to another power factor. So, these are certain things we found, and the dead time effect and the compensation is just the other side of the coin. If you know what is the effect of the dead time, you can compensate for that. We found that it basically introduces certain kind of error voltage. You can compensate for that error voltage by adding the negative of it, equivalent, what is equivalent to the negative of the error voltage to the modulating signal. So, though our emphasis was entirely on the inverter dead time, the compensation is just one step away. So, we could do that. So, here we are going to look at something what is nonlinear. Here firstly what we found was the effect of that is the fundamental voltage is no longer proportional to the reference, because that is the ideal fundamental voltage. On top of the ideal fundamental voltage there was a small component that was getting added, which is the fundamental error voltage caused by dead time, and whatever you are getting is the phasorial sum of these two, the ideal fundamental voltage and the error voltage fundamental voltage because of that. So, you have the phasorial sum. Now, we are going to look at something where the ideal fundamental voltage itself is not proportional to your voltage reference. We are going to go into the nonlinear region of operation of PWM rectifiers, that is where your reference might not really be the inverter voltage may not be proportional to that. So, why do you have to do that? See, we can trace it back to sine-triangle PWM. With sine triangle PWM, very simple way of doing things. So, you can calculate, you can modulate the AC side voltage reasonably good harmonic spectrum. But we went in for common mode injection. Why did we go in for common mode injection? Among the various reasons, one reason why we needed to do that was to increase the DC bus utilization. So, we increase the duty bus utilization. Now, with sine triangle PWM, the maximum fundamental whatever you could get was 0.5 VDC, the peak phase fundamental voltage was VDC by 2. When we went for common mode injection or certain kinds of appropriate common mode injection, we could increase VDC by 2 to VDC by root 3, that is 0.577 times VDC. Now, by adapting to overmodulation, you can take your inverter all the way till square wave mode, which can give you 2 upon pi times VDC or 0.644 times VDC. That is what we are trying to do. So, why do we need overmodulation? In one sense, it is to increase the DC bus utilization further. That is, if you resort to overmodulation, now you can produce higher AC side voltage. At what cost? The same DC bus voltage. Since the DC bus voltage is same, the device voltage ratings are also same, no problem. So, with the same DC bus voltage and same device rating, you are able to have an inverter whose voltage rating is higher, whose AC voltage rating is higher. But there is a problem, it introduces low frequency distortion in your output. Therefore, there are going to be low frequency currents, and that is going to lead to several problems. In closed loop control, it is going to be much more difficult to handle that. Okay. So, these are some things that we will look at now. So, today's and the next lectures would exclusively focus on overmodulation now. Today's lecture would focus on the overmodulation for triangle comparison based PWM. We try to get an understanding of that problem, and in the next class we would do some space vector algorithms for overmodulation and so on. And then the last one we would be for this PWM for multi-level inverter. All that we have been able to study for this 2-level inverter, we should be able to extend them to 3-level inverter, and we will do a few things, some triangle comparison based PWM and some space vector based PWM, their analysis for multi-level inverter now. So, after this rather long introduction to this, let me take you to this present module in greater detail. So, I said I am going to deal with overmodulation. So, what we are going to first do is to review sine triangle PWM. It is better that we pick up our threads from there, and then let us review these quantities what we have called as average pole voltage, average line to line voltage, and average line to neutral voltage, and average two phase voltages. So, then what we would essentially do today is this analysis of sine triangle PWM during overmodulation. So, when there is an inverter, it is feeding a load, let us take it as an induction motor load for example, and that inverter is having a DC bus voltage, it is operating in overmodulation, that is its peak value of sine is greater than the peak value of carrier. So, what happens? That is what we are essentially going to see now. So, how would we look at that? What do you mean by what happens? So, what are the quantities you will look at? We will look at the average pole voltage, we will look at the average line to line voltage of the inverter. We will also look at the average pole voltage and the average line to neutral voltage applied on the load during this overmodulation. We will just see what happens to these waveforms. They will not be sinusoidal, that is certainly you can understand. And then once you have this average 3 phase voltages, you can transform them into average 2 phase voltages. This is space vector transformation. Now, we will look at how these 2 phase voltages vary during overmodulation. Now, you have come to the 2 phase voltages, which are basically the orthogonal components of the voltage space vector or the average voltage vector. Now, we will see how the magnitude and angle of the average voltage vector are. They will not be, for example, the magnitude of the average voltage vector cannot be expected to be constant throughout the cycle. That is the case in linear modulation. In linear modulation, at a steady operating condition, the average voltage vector has a constant magnitude, which will not be the case for example in overmodulation, right. So, you will have some things like, so we will look at how that magnitude varies, and that itself might vary differently in different regions of modulation. From sine triangle PWM, you slightly go into overmodulation, it may be different. When you go into deeper into overmodulation, closer to 6-step mode, it can be different. So, we will look at that. We will also look at how does the angle of the average voltage vector vary in different regions of that. This would essentially give us an idea on how to deal with overmodulation, what is overmodulation, how to deal with overmodulation, and this analysis in the space vector domain will be giving us enough inputs, enough thoughts on how we can handle overmodulation when we are dealing with space vector modulated inverters. Alright. So, in the next lecture what we will probably do is we will take it up from that. We will review conventional space vector PWM as a common mode injection PWM, and we will do a similar analysis of what we are going to do today for sine triangle PWM. We will do the same thing for conventional space vector PWM, and we will go look at the average pole voltage, average line to line voltage, average line to neutral voltage, and we will transform them into the two phases, and then we will see that we will come very close to certain space vector based methods of doing them now. As a result of all this, we will be able to understand how to implement overmodulation in space vector based PWM. We will discuss a few algorithms, overmodulation algorithms for space vector based inverters, and do some analysis in the synchronously revolving reference frame. This is what we would probably do in the next lecture. So, now coming to the today's purpose, we are going to deal with voltage source inverter. So, we are going to deal with a voltage source inverter which has a fixed DC bus voltage VDC, and which is modulated using sine triangle PWM, and it is modulated such that it is the inverter is an overmodulation, that is the peak of the sinusoidal voltages they are greater than the peak of the carrier. So, that is overmodulation. So, we are going to analyze this overmodulation, and how are we going to analyze? We are actually going to analyze it from the space vector perspective. So, that is what we are going to do today. Let us get started. So, this is the inverter. Now, you have two legs which are switched in the complementary fashion, and we are going to ignore dead time today once again, like we did the analysis for the linear modulation, because our focus here is now understanding the difference between linear modulation and overmodulation. Alright, and what is going to happen is now, so there is a 3-phase load, we can presume it to be maybe an induction motor, and you have this now. So, we are going to look at these basic quantities. So, it's better that we take a good quick recap of that. So, this is R midpoint, this is a load terminal, midpoint of this leg. VRO is the pole voltage. So, R, this midpoint of R phase leg measured with respect to O. Similarly, VYO is the Y phase pole voltage at this point measured with respect to O. VBO is the B phase pole voltage, that is measured at B with respect to O. So, these are pole voltages, 3-phase pole voltages. VRY would be the line to line voltage, VRO minus VYO will give you that. Similarly, VYO minus VBO will give you VYB, and VBO minus VRO will give you VBR. So, these are the line to line voltages, and then there is a 3-phase load. We assume it to be a balanced star connected load and whose neutral is N. So, there is VR with respect to the load neutral N, and Y with respect to load neutral N, and again B may with respect to load neutral N. So, these are the various 3-phase voltages. The same 3-phase voltages can actually be represented in terms of the pole voltages or the line to line voltages or the line to neutral voltage applied on that now. So, to recap, let us go to a DC-DC chopper. What do we want here? We want this voltage. So, you want certain output voltage. There is some average output. The input is V in, we want an output V out, which is let us say 50% V in or 80% V in or whatever, it is something lower than that. Now, this is an inductive filter. So, whatever is the average voltage you would want the same average voltage here now. And how should that average voltage be? That is, we call this VP, and that VP average should be horizontal line. What is this VP average? If P is connected to throw 2, it is 0. If P is connected to throw T1, then the voltage is whatever comes between, that is V in comes here. So, it is sometimes equal to V in and sometimes equal to 0, and you might be switching it at some duty ratio D. So, it is V in into D, that would be the pole voltage, average pole voltage in this case. Now, you want DC output. So, you want the pole voltage to be equal to your desired DC voltage. So, this is how you want it to be in the case of a DC-DC chopper now. And if you want this, how do you achieve that? You achieve that by having a carrier signal and a control signal like that, and you compare the two, and these would be your gating pulses that are fed to the active device. So, if you want more amount of fundamental voltage, higher duty ratio, you take this up. If you want lower, you just bring this down. So, you achieve this by comparing a DC modulating signal with such carrier to produce this now. What is the situation in a sinusoidal inverter? Here 3-phase voltage, you desire a sinusoidal voltage between VRY, again you desire VYB. So, again between VBR you desire sinusoidal voltages. Like you can look at average voltage VRY average. What do you mean by VRY average? Averaged over a subcycle, and similarly VYB is VYB averaged over a subcycle. We want these waveforms to be sinusoidal. You can ensure these to be sinusoidal if VRO average is sinusoidal, VYO average is sinusoidal, and VBO average is sinusoidal. Okay. So, you further want these 3 to be 3 phase symmetric, VRY average, VYB average, and VBR average. So, you can achieve this by having VRO average to be sinusoidal, VYO average to be sinusoidal, and VBO average to be sinusoidal and also symmetric. So, what we actually want is we would want the VRO to vary like that. So, in one subcycle this is your VRO, the next subcycle this is your VRO, in the third subcycle this is your VRO, fourth subcycle. So, this VRO average goes on increasing subcycle by subcycle. Here when it goes on increasing, what it effectively means is the top device is on for a longer time and the short is on for shorter time. So, here the duty ratio is maximum. Again it reduces and comes back to close to 0. When it is close to 0, the top and the bottom devices are both on for equal durations of time, and then you go down, and when you have your most negative VRO average, your duty ratio is your minimum, and then it goes back now. So, you switch that in such a fashion that in different subcycles the average values are different, and these average voltages vary in a sinusoidal fashion, they vary in a sinusoidal fashion. And how can you ensure this? If one that you can ensure by comparing triangle with sine, as we will see now. If let us say you are able to you produce such a VRO average and a VYO average as given by this phasor and VBO average given by this phasor, then you can get your VRY average as desired by the difference between that. Again VYO average minus VBO average will give you this VYB average. Again this VBO average minus VRO average will give you your VBR average. Alright. This should be, there is an error here. This should be VBR average. Thank you. So, you ensure them, you want these to be sinusoidal. So, you want these line to line voltage to be sinusoidal. One way of ensuring, but not necessarily the only way, is to make sure that VRO average and VYO and VBO average are sinusoidal as shown by these phasors. Alright. So, how do you get them? You define modulating signals MR, MY and MB, and you compare them with a high frequency triangular carrier which goes up and down like this, and the triangular carrier has not been shown in this figure. So, whenever the modulating signal is greater than the triangular carrier, the top device is on, otherwise the bottom device is on. So, it goes on like that. Alright. So, you go about doing this. So, this is a particular, I am showing only one R phase signal and I am showing the triangular carrier. Of course, the carrier is shown to be of lower frequency here, this is only for illustrative purposes, and typically the carrier frequency would be much higher than what it is being shown now. So, now if you look at R phase, the top device can be on or the bottom device can be on. So, accordingly VRO can be either plus VDC by 2 or minus VDC by 2. Similarly, VYO can be plus VDC by 2 or minus VDC by 2, VBO can also be plus VDC by 2 or minus VDC by 2. So, VRY equals VRO minus VYO, VRN is equal to VRY minus VBR by 3, assuming 3 phase balanced load. So, this is how your, these are pole voltages, these are line to line voltages, you similarly you have VYB and VBR, these are line to neutral voltages applied on the load, phase to neutral voltages applied on the 3 phase balanced load now. So, how you can do a space vector transformation. Once you have VRN, VYN and VBN which add up to 0 like this, you can have some V alpha which is equal to 3 by 2 times VRN and V beta which is equal to root 3 by 2 times VYN minus VBN. This is what we have seen before. So, next what we can do is, we will start looking at the average quantities, averaged over the subcycles. So, now you have MR, MR is Vm sin omega t, a sinusoidal modulating signal for R phase, My sinusoidal modulating signal for Y phase, same amplitude, same frequency, phase shifted by 120 degree. Mb is the sinusoidal modulating signal for B phase, same amplitude, same frequency, phase shifted by 240 degrees from MR. So, this is what you have now. Now, you are going to compare them with carrier and then produce the signals and do that. So, your VRO average, what will your VRO average be? It will be MR upon Vp times VDC by 2. So, if MR is equal to Vp, it will be VDC by 2. If MR is equal to minus Vp, this will be minus VDC by 2. So, this VRO average will be anywhere between minus VDC by 2 and plus VDC by 2. It cannot exceed plus VDC by 2. That is what is going to cause a change here now. Even let us say you have MR is equal to Vp, you will restrict MR to Vp when you are doing your linear modulation. In your overmodulation, this MR will go higher than that, but even if it goes higher than that it will not cross, that is what is not exactly shown here, but this has been written more in the context of linear modulation. VRO average cannot exceed plus VDC by 2 and it cannot go below minus VDC by 2. Similarly, VYO average during linear modulation is MY by VP times VDC by 2 and the VBO average is also MB by VP times VDC by 2. When B phase modulating signal becomes higher than VP, VBO average is clipped to plus VDC by 2. When MB becomes lower than minus VP, then VBO average is clipped to minus VDC by 2. Alright, then what is VRY average? Whatever is VRO average minus VYO average. The same way you can define VYB average and VBR average, and VRN average is 1/3 of VRY average minus VBR average. So, now you look at this VRN average, this VRN average will be actually Vm sin omega t by Vp into VDC by 2, which is equal to VRO average if you are looking at sinusoidal modulating signals. So, if you are using sine triangle PWM and you are in linear modulation, then VRN average and VRO average are equal to one another. What happens if you have common mode added? This will contain the common mode components and this will not contain the common mode components, as we will just see now. Alright. So, this is a case where common mode has been added, 3 phase sinusoidal modulating signals as before, some common mode signal MCM has been added to all these 3 to get MR star, MY star and MB star. Now, MR star is compared with the carrier to produce PWM waveform, similarly MY star and MB star. So, your VRO average will be MR star by VP into VDC by 2, but this is valid only as long as MR star is within plus VP and minus VP. If MR star for some reasons goes beyond plus VP, as it happens in overmodulation, then this will be equal to VDC by 2. Similarly, it may MR star might go lower than minus VP, in that case that will get clipped to minus VDC by 2. So, this expression is exactly valid for linear modulation. If it is overmodulation, then if MR star greater than 1, then or greater than VP, VRO average is plus VDC by 2. If MR star is less than minus VP, it is equal to minus VDC by 2. That is the difference it will essentially make. And so, this is your VIO average, which depends on MY star, and it is basically you need to scale the modulating signal with respect to the carrier peak and you multiply by VDC by 2, that is what it is. Similarly, it is MB star by VP into VDC by 2. What is your VRY average? It is VRO average minus VYO average. Now, you see when you are doing this, you are actually subtracting MR star minus MY star, the whole by VP into VDC by 2. When you subtract MR star minus MY star, there is MCM here and there is also MCM here, that gets cancelled. So, that gets VRY average will not contain the common mode components at all, and then when you do your VRN average, you will come out to VRY average minus VBR average, the whole divided by 3. So, your VRN average would contain only the fundamental component and the common mode components which were present in VRO average would now be absent. So, they are not exactly equal. So, if you are looking at linear modulation, VRO average will be an exact replica of your modulating signal, it is a scaled version of your modulating signal. It would contain the fundamental and the triplet frequency components, whereas VRN average would contain only the fundamental components, it will not have the triplet frequency. However, if you are going into overmodulation, all these will be non-sinusoidal. VRO average will be non-sinusoidal and therefore RY average will also be non-sinusoidal, VRN average also will be non-sinusoidal, as we will see now shortly. So, once you have these 3 phase average voltages, again this is what is VRN average, this instantaneous VRN has been averaged over one subcycle. Similarly, VYN has been averaged over one subcycle, VBN has been averaged over one subcycle. Now, you add, you do your space vector transformation on VRN average, VYN average and VBN average. So, this is your space vector transformation and this gives you what is called as V alpha average and V beta average. These are the components of the voltage space vector of the average vector. So, this is V alpha average and V beta average now. So, these are, so we will start referring to them as 2 phase voltages. So, when we say 2 phase voltages, we have used this term before also, but we have not used these term in a number of lectures in between. So, whenever we use the term, what we mean is basically the 2 components, the 2 orthogonal components of the average voltage vector along alpha axis and the beta axis. Alright, so these are 2 phase average voltages. Now, when you go into overmodulation in sine triangle PWM, what do you mean by this? Let us put our basic understanding in. Overmodulation sets in when the peak of the sinusoidal signal exceeds the carrier peak, which is obvious, which is the starting point. So, what we would expect? We would expect the average pole voltage to become non-sinusoidal. Why? Because the modulating signal goes above V peak. Whenever it goes above V peak, average pole voltage will be clipped to plus VDC by 2. Similarly, when the modulating signal goes below minus V peak, this will be clipped to minus VDC by 2. So, a clipped sinusoidal waveform, right, a peak clipped sinusoidal waveform is certainly not sinusoidal, it has low frequency harmonics, it will have third, fifth, seventh and what not. So, you would expect your average pole voltage to be non-sinusoidal. When average pole voltage is non-sinusoidal, and particularly when the average pole voltage could contain components other than the triplen components, it is not going to contain only third, ninth, it is going to contain fifth, seventh, 11th, 13th also. In that case, the average line to line voltages will also have harmonic components, and when they have harmonic components, the line to neutral voltages applied on the load would also have those harmonic voltages. So, these will be low harmonics. So, the load will get something like, apart from the fundamental, it will have some 5th, 7th, 11th, 13th kind of harmonics applied onto this. That is because of overmodulation. These are certain things that we can expect, it is just common sense. Average voltages, now what we are going to look at, we are going to look at these, look at certain cases, particular examples and see how they are varying and get a clearer understanding, and we are going to look at this in the space vector domain. We are going to see if these kind of in non-sinusoidal average voltages are transformed into the space vector domain, how are they going to look at is one of the things that we are going to look at today. Okay. So, let us get inside now. So, this is overmodulation, you see I have get m is equal to 1.1. What is m here? Here m stands for the ratio of the peak of the sinusoidal signal to the peak of the carrier. I am taking the peak of the carrier to be 1 here and the peak of the sinusoid is 1.1, alright. So, you see that it goes higher than the carrier peak here, again it goes below that here, and the same story is the same thing is true for all these 3 modulating signals. So, this is one example of overmodulation. I would say you are not deep into overmodulation, you are slightly into overmodulation. What you have done is you have just gone above, little above that. One is permissible, you have gone a little above that. Now, let us see what happens. This is clipped, this is should have been sinusoidal ideally, but this is clipped. Why? That is because it is plus VDC by 2, it cannot exceed plus VDC by 2. Similarly, it is clipped here. Why? Because minus VDC by 2 is the most negative average pole voltage that can be applied. The bottom device is continuously on, and therefore, your pole voltage is minus VDC by 2 throughout a subcycle. In that case, the average pole voltage is minus VDC by 2, it cannot be more than that. The same way you can see that R phase, it is true about Y phase, it is true about B phase. So, we are going to look at these things. Here, our depth of overmodulation is not very high, I would say. So, let us see. This is the region, during which R phase is not switching. So, you will see pulses on the R phase PWM waveform here, but you will see no pulses here. The top gate device will be continuously on. Similarly, if you look at the R phase PWM pulses, you will see that it is continuously off here. The top device gating signal will be continuously low, the bottom device gating signal will be continuously high. And so, there are pulses here and there are no pulses here, and that is why it is called pulse dropping. So, this pulse dropping begins. At this kind of a modulation index 1.1, there will be only one per phase which will undergo pulse dropping at a given point of time. If this increases, 2 phases may come. For example, here it is pulse dropping for R phase, pulse dropping for B phase starts a little later and goes on till then. The pulse dropping for the Y phase starts a little later now. So, this is the nature of your 3 phase pole voltages. Now, you go about the procedure is clear, I have already delineated the procedure. So, when I subtract that, what happens now? Now, you look at these are sinusoidal voltages now. So, what has happened between earlier thing and now? Whatever were the harmonic components, the triplen ones have got knocked off, they have been removed, and all the other components like 1st, 5th, 7th, 11th, 13th etc., they get multiplied by a factor root 3 and they are here. If you do a harmonic analysis of this, you will find fundamental 5th, 7th, 11th, 13th etc., and these harmonic amplitudes will be root 3 times the corresponding amplitudes for VRO average etc. So, you have your signal like this. Now, you can certainly see that it is non-sinusoidal, it is kind of going and saturating here somewhere here, it is lower than 1, 1 stands for the DC bus voltage VDC. So, it is a little lower than 1, so it goes somewhere there and it comes around like this now. The same way you have this V RY average, this is VYB average, and this is VBR average. Okay. Now, let us go back. So, what is this? This is VRN average. This is the average line to neutral load voltage now. So, this is not exactly clipped, you see that it is slightly going above 0.5. So, this is VRN average, and this is this VYN average, and this is VBN average. You should have ideally applied sinusoidal voltages here, but instead of in the linear modulation this should have been sinusoidal. Instead of that, there is certain amount of harmonic distortion in these waveforms. These are low frequency distortion, like 5th, 7th, 11th, 13th kind of components are here, and these are going to cause corresponding harmonic currents and could cause pulsating torque and other issues here now. So, if we transform now, for example, that VRO average and VRN average are not exactly same, that is what I was trying to tell you. So, this blue waveform is the VRO average, you can see that it is flat here and that is at 0.5 VDC, whereas the VRN average slightly goes above that, here it goes below this now. So, the difference between the two lies in the triplet frequency component, is some small amount of triplet frequency component which is there in VRO average is not there in VRN average. So, you get that there now. So, we transform those 3 phase voltages VRN average, VYN average and VBN average to get V alpha average. What is this? V alpha average, and this is V beta average. Very clearly these are non-sinusoidal, and therefore, what happens? The magnitude and the angle. So, ideally these should be sinusoidal, and if these are sinusoidal, the magnitude of the voltage vector will be constant and the voltage vector will move at a uniform speed. Now, what happens? The magnitude varies like that. When m is equal to 1, when m is equal to 1, this would have been, I will take a different color so that it does not mess up with that. At m is equal to 1, this is not, I am not drawing it very clearly, it should be really above this. This is how it would have varied, and this would be constant, and it will go to like, okay. So, this is for m is equal to 1. So, this one will be actually equal to 0.785, which is pi by 4. So, that would have been your voltage, that would have been the average value of the vector now. But once you cross that, what happens? The magnitude goes on changing like this. You can see a ripple on that magnitude, it is not constant now, and you can see that it is actually 6th harmonic. Every 60 degree it repeats. So, it is repeating in every sector. Therefore, you look at only one sector, you can see that this is how it varies. This is sector 1, where omega t equals 90 degree stands for the positive peak of R phase voltage, and omega t is equal to 150 degree stands for the negative peak of B phase voltage. So, this sector I am just showing here, you can see that the magnitude is no longer constant, it is varying with the fundamental angle. Alright. Now, how about the angle? The angle of the vector is more or less linearly with time. So, the angular velocity is more or less constant. Let us go further. So, what does it really mean? Let us say if we are looking at linear modulation, this would have been a circle like this. This would have been circle, and in the different subcycles you would have applied vectors like this. Now, what is happening? You may have applied some vector like this and some other vector like this, again some other vector like this. Let us call this as Vref1, let us call this as Vref2, let us call this as Vref3. Now, the magnitudes Vref1 is not equal to the magnitude Vref2, and that is not equal to magnitude Vref3. This is because of overmodulation. This is what our analysis shows. And the next thing, these angles that you may have between that, let me use a different color to indicate the angle. This angle, why is it back to that in color? Okay. This angle and this angle, they are more or less equal to omega ts. The angles are almost approximately equal to omega ts, also this angle. So, the vector this magnitude is changing, it is not really sinusoidal, it is changing somewhat, but it is still moving at a uniform velocity, that is what it means now. So, let us summarize some of our findings for this region. Whatever we found is true for this region 1 less than m less than 1.15. So, 1.15 is actually 2 upon root 3, that is what I have written as 1.15. Now, if you are taking a modulation index like this, no modulating signal or only one of the 3 modulating signals would exceed the carrier peak in a given carrier cycle. So, that is at best 1. So, that one will be clamped, the other 2 will continue to switch. Sometimes all the 3 might not exceed, and therefore, all the 3 might switch. So, you will see that 3 phases are switching or maybe 2 phases are switching, and if you look at a phase, you will see that the pulse dropping has started. And where does it start? It starts around the peaks of the fundamental voltage, that is where the sinusoidal signal goes beyond the carrier. So, the pulse dropping of each phase would start around that, and you will see that pulse dropping now, but the overall pulse dropping duration will be like less than 60 degree in length. So, the worst case could be like from 60 degree to 120 degree for R phase, that will happen when you are looking at m is equal to 2 by root 3. Now, because of this, what happens, the VRO average is a peak clipped sinusoid, and therefore, there is some average pole voltage, there is some distortion here, and therefore, the same distortions, but for the triplet frequency components are carried over into the line to line components and into the phase neutral components. Because of this, what happens, the magnitude of the average voltage vector varies with fundamental angle, it is no longer constant, it varies. Then what happens further? The trajectory of the tip of the average voltage vector is non-circular. I mean, if the magnitude has been constant, then its trajectory would be circular. Now, if you look at the tip of the average voltage vector, one subcycle, average voltage vector in the next subcycle and the subsequent consequent subcycles, you plot that the trajectory will not be circular, because this magnitude is no longer constant. Then you look at the angle of the average voltage vector, it varies almost linearly, there is a small approximation there. So, it is almost linearly with time, you can say it is more or less linear, there is nothing, there is not so much of deviation here, but as you go to higher and higher modulation indices, you will see there is more deviation, and at close to the very high modulation indices, close to 6 step, you will see that this is no longer really linear, but it becomes closer to piecewise linear. Alright. So, now I am going to consider another example of 1.2. So, when I have taken 1.2, what happens here, R phase goes above the signal peak value. Let me just draw some lines there, so that, so where does R phase go above the peak? So, in this region R phase is above, so in this region you can see partly this Y phase is also lower than -1. So, there is going to be a small region where both of them are going to be clamped, for example here. In this region you will see that both of them are going to be clamped, the same way here. I have not drawn this very accurately, you will also find a band here. So, during these intervals both the phases are clamped. So, whereas in this interval only R might be clamped, in this interval both R and Y, here maybe R and B, and here only B phase is clamped. So, it goes beyond this now. So, what happens to the average pole voltage? Clipped to 0.5 VDC, here it is clipped to minus 0.5 VDC. This looks roughly trapezoidal, because this is a linear, this is a sine waveform, close to 0 crossing looks more like a straight line. So, it is roughly trapezoidal, this is R, Y and B, VRO average, VYO average and VBO average now. So, this has triplet frequency, 5th, 7th and other harmonics. When you do this, when you go to the line to line voltages, the triplet frequency components are absent, and you can see that these waveforms look more sinusoidal than, for example, this waveform. That is because the triplet frequency components have gone, and therefore, it looks more sinusoidal, but you can very clearly see that it is no longer sinusoidal. It is much worse than when you saw that at m is equal to 1.1. If you do a harmonic analysis, you will see that 5th, 7th, 11th, 13th etc. would have increased in some sense. So, this is VRY average, VYB average and VBR average now. So, from here let me go to VRN average, VYN average and VBN average. You can see that there is a significant amount of low frequency distortion has set in now. So, here to distinguish between VRO average, this is VRO average and this is VRN average. So, VRN average is a little more rounded and goes slightly above 0.5 VDC and does not contain triplet frequency components, whereas VRO average is clipped at 0.5 VDC and minus 0.5 VDC and looks more trapezoidal in nature. Alright. So, when the 3 phase average voltages are transformed into the space vector domain, your V alpha average is like this. You can see that V alpha is kind of flattening here, and here also it is flattening here, and you can see this V beta average, you can start seeing some kind of straight lines here. Every 60 degree you can start seeing the straight lines. So, a little later this will actually become exactly straight lines, and this will also probably become straight line like this. You will see this becoming a trapezoidal one, and you will see that this is all piecewise linear lines at a slightly higher modulation index than now. So, if I have considered this V alpha average and V beta average, you will look at the magnitude. What is the magnitude? V alpha average square plus V beta average square under root. If I do that, this is how the variation is, whereas the average voltage is somewhere in between that. It is somewhere between, it is above 0.8, and this is now going like this. So, this is 0.866 to 0.8, that is the variation here. If the highest value is yeah, it should be 0.866. No, you cannot say that, you have to look into that and see this now. So, you get this kind of variation, and you can see that the voltage vector is actually constant here, and it kind of varies here. Alright. So, now this is periodic over every sector. So, it is enough we are going to look at one sector. So, we are going to look at this 90 to 150 degrees, which is what we call a sector 1. So, this corresponds to the positive peak of R phase, so this corresponds to the negative peak of B phase, and here we find that this is how it goes. Alright. Okay. So, this is the magnitude of average voltage vector over a sector now. Now, it is no longer constant. How about the angle? Angle still rises reasonably linearly with this thing. If you plot the constant straight line joining these 2 points, you may see some slight deviation between the two, but that is not very high. It is still more or less a straight line, and you can say that the average voltage vector is moving at a uniform angular velocity. So, if I look at the voltage vectors, what happens now? I might come to slightly higher modulation indices. Like this. You can very evidently see that if I call this Vref 1 and I call this Vref 4, their magnitudes are very, very different. Magnitude of Vref 1 is not equal to magnitude of Vref 4 or Vref 2, whatever the other things that you can really look at now. So, the magnitudes go about changing, but how about the angles? The angles are still, these angles are still equal. How much they are there? That is equal to omega ts. This angle is also roughly equal to omega ts, may not exactly be, but it is roughly equal to omega ts. This is how the nature of variation is. So, now I am going to look at this 1.15 to m, this m I mean to 2. So, this is the range now. So, for this range now 1.2 was really representative. What happens is 1 or 2 of the 3 modulating signals, they exceed the carrier peak in a carrier cycle. You consider any arbitrary carrier cycle, you will sometimes find one modulating signal exceeds the carrier peak, sometimes you will find 2 modulating signals exceeding the carrier peak now. So, this pulse dropping is there. So, pulse dropping is for longer than 60 degree duration, but shorter than 120 degree duration. In fact, if it is 1.15 or 2 by root 3, your pulse dropping duration will be 60 degree for each phase in each half cycle. If m is equal to 2, you will see that the pulse dropping duration is 120 degree for each phase in each half cycle. This FIR must be FOR, you could correct it now. FOR, alright. So, low frequency harmonic distortion. There is low frequency harmonic distortion, but it is quite pronounced when compared to what you found at m is equal to 1 or in the range 1 to 1.15. Now, it is much more pronounced and goes on increasing as m goes from 1.15 to 2. Now, if you look at the magnitude of the average voltage vector, it varies with fundamental angle, and this variation is also more pronounced than it was in the range 1 to 1.15. Again, the trajectory of the tip of the average voltage, because this magnitude is varying, the tip of the average voltage vector, its trajectory is no longer circular. I mean, it is more non-circular than it was before, if I can use the term. Then angle of the average voltage vector, however, continues to be almost linear with time. So, it is more, still it is more or less equal now. So, let us look at the particular case of m is equal to 2, where you can see that this is the peak of the carrier, you are going twice the peak of the carrier now. So, what is happening is, this is 0 to 30 degree, from 30 degree to 150 degree R phase modulating signal is higher than the peak. carry, I mean the triangular peak. And similarly you can look at here also, it is from 210 to 330 degrees. The same way you have for y phase and b phase now. So this 120 degree you will see that, for example, you take this 30 to 90 degree, r phase exceeds the positive peak of the carrier, the same 30 to 90 degree the y phase exceeds the negative peak of the carrier. Similarly here r phase exceeds the positive peak of the carrier, here b phase exceeds the negative peak of the carrier. So two phases are clamped concurrently in any carrier cycle, which two depends on what is the angle of your fundamental now. So that you can, this will be evident from this figure. This is how is your VRO average pole voltage, and now this is your VBO average and this is your VRO average. They all look almost trapezoidal waveforms, because this is sinusoidal actually, but sine around the 0 crossing is more or less a straight line, the sin theta is approximately equal to theta, therefore sin x approximately equal to x, therefore you get this kind of thing here now. So when you do this you get something, these are the VRY average, VYB average and VBR average. These look a little more sinusoidal than the previous ones, but nevertheless you can see that they are flat. What do you mean by they are flat really? It is VDC. So during this region this is RY is equal to VDC, VRY is equal to R phase is always connected to the top device, Y phase is always connected to the I mean the bottom switch is always on. So VRY is always positive here. And if you take this region for example, or take this region, what is this? This is VBR. VB is the lower device is always on and R phase the top device is always on. And similarly you look at here VYB is VDC. So VY top, Y phase top device is always on and B phase bottom device is always on during this now. So you can see that they have started switching lower and lower. So actually for R phase, you know, any particular phase for 120 degree it does not switch, it switches only during those 60 degrees around the 0 crossings, the first 30 degree and the last 30 degree in every half cycle. So you see that there is more distortion. And now these are the VRN waveforms, VYN average and VBN average. You can see that they are almost like straight lines, piecewise linear lines. And VRN average and V alpha average is nothing but this is the comparison of VRO average and VYN average, where VRO average is trapezoidal, VRN average looks like this, it is a piecewise linear line, and the triplet frequency components are absent here. This is at m equals 2. So this is V alpha average. V alpha average will look very similar to VRN average. Why? Because V alpha average is 3/2 times VRN average, is just 1.5 times that, and so you get the same waveform here, and this is your V beta average now. So you can start seeing that, you know, these are flat and this is a straight line for 120 degree, it rises flat for 60, falls for 120 degree linearly, again flat for 60. Here what happens, it rises at double the slope for 60, at some single slope for 30 degrees, for 60 degree, again single slope for 60, it falls, double slope for 60 and again single slope for 60 degree duration. This is how the nature is now. So if you look at the magnitude is no longer constant, but the magnitude just goes on varying like this. The variation in the magnitude is very much pronounced. So it varies like this. And if you look at just one sector, the magnitude starts from 1 and goes and ends here now. So what happens now? But if you look at angle alpha, this alpha is varying like this. It is still more or less linear, as I said before. So what happens? Now how are the vectors looking like? If you go to the earlier slide, the angle goes on changing linearly. So what it does mean is in every angular step now, for example, if I have one, if I have, this is the reference vector in the first one, this is the reference vector in the other one, these are all uniformly spaced is what it says. The reference vectors are still uniformly spaced, though I am not able to draw it as neatly. So they are still the same spacing, it is moving at the same thing, but what is the length of these reference vectors? Obviously you cannot be producing reference vectors longer than that. You can very clearly see what is the magnitude. This is 1, this is 1 and it goes on like this. So the magnitude of the average voltage vector is really changing like that. What exactly happens, alpha changes, the magnitude is falling like this. What it exactly means is it stops here. Let me choose a different color. this is this is how the vectors are. This is how the vectors are. There is no null vector at all applied. Is that clear? How can you say that? You can see that only one phase is switching. Which phase switches? Now this is 90 to 150 degrees, right? So the only phase that switches will be Y. R is not switching and B is not switching. If you want, you can go back here and look at this 90 to 150 degree. Let us look at the average pole voltages. This is 90 to 150, R phase is not switching. Again 90 to 150, B phase is not switching. Who is switching? Only Y phase is switching, and therefore the voltage has been switching between this active vector plus minus minus and plus plus minus. So the resultant active vector, its tip will always lie on this. If T1 is applied for longer durations, it will be closer here. If T2 is applied for longer durations, it will be closer here. This is what happens now. The next interesting variation is if you go to m is equal to 3, beyond 2 what happens? It is clipped for longer time, not 120 degree, it is longer than 120 degree. So you get your average line to line voltages varying like this, and if you look at your V alpha average and V beta average, they go about doing like this. So this is your VRO average and VRO average and VRN average. So you can see that it is here clamped to some peak values and here it is clamped to peak values, and this is actually 0.5 VDC, this is 2 by 3 VDC, this is VDC by 3, this is also VDC by 3. So if you look at the magnitudes are 1. If what do you mean by magnitude being 1? An active vector is actually being applied. Here it is another active vector is being applied. So if you look at just one sector, up to this its active vector 1 is being applied, and then here active vector 2 is applied, and what is happening in between? There is switching between active vector 1 and active vector 2. So in all these subcycles you switch for active vector 1 and 2 only, null vector is never applied. And so, but if you look at the angle, because active vector 1 alone is applied here, it is not moving at all, it is 0. Here active vector 2 alone is applied, it is not moving. In between it moves more or less like a straight line, not exactly, but this can be approximated as a piecewise straight line. Therefore when you go close to that, the range m greater than 2, this PWM what it does is it moves little like, first it is here for a longer time. Let me choose a red color. So it stays here for a number of, then it moves like this, then it moves like this, then finally it goes and stays here, it stays here. That is how the average voltage vectors are moving. So this is very important for us to understand how it is going to operate in the in the voltage space vector plane. So this is I have illustrated the average line to line voltage as square wave form. So you can see that it is average pole voltage for square wave, and these are the line to line voltages, and these are the two phase average voltages. In the case of square wave, what exactly happens is only one vector is applied. This vector is applied for entire 60 degree duration, this vector for another 60, this vector for another 60, this is for another 60, this is for another 60, this is for another 60. That is square wave operation now, and these are good references for you. Firstly, especially these 3 references, all these 3 references deal with the analysis that we presented today. So this is a chapter in the thesis, and there is a conference paper, and this is a later journal version of this paper. So I would suggest this as your references. There are other references for the next part of our lecture, so which I would discuss about in the next lecture. So thank you for your interest here, and I hope this was useful to you, and I hope to have you again in my lectures. Thank you very much. Bye.